Derating conductors involves reducing the current carrying capacity below their standard ampacity to account for specific operating conditions or factors that can affect their performance. This is necessary to ensure the safe and reliable operation of electrical systems. Conductors are derated for various reasons, including continuous load, high ambient temperature, multiple conductors in raceways, overcurrent protection devices, and conductor material. Motors and other equipment that operate continuously for extended periods generate heat, which can increase the temperature of conductors and reduce their current carrying capacity. If conductors are installed in locations with higher than normal ambient temperatures, such as in attics or close to heat sources, the current carrying capacity may need to be derated. When multiple conductors are bundled together in conduit or raceways, they create closer proximity and generate more heat, necessitating derating. The rating of the overcurrent protection device protecting the circuit may also affect the required derating. Different conductor materials have different temperature ratings and may require different levels of derating. The National Electrical Code, specifically Article 310.15, provides guidance on derating conductors based on the operating conditions and installation method. It includes tables that list the derating factors to be applied based on the number of conductors in the raceway, the ambient temperature, and the conductor material. To derate conductors, follow these steps. Firstly, determine the current rating of the conductor from its ampacity table. Secondly, identify the derating factors applicable to the installation conditions. Thirdly, multiply the conductor's ampacity by the derating factor or factors to obtain the derated current carrying capacity. Fourthly, use the derated current carrying capacity to select the appropriate conductor size for the application. Let's explore each of these in more detail. Firstly, continuous loads require special consideration when sizing conductors. The National Electrical Code defines a continuous load as a load where the maximum current is expected to continue for 3 hours or more. Because of the sustained current flow, conductors supplying continuous loads are subject to heating, which reduces their current carrying capacity. To account for this, the National Electrical Code requires that conductors be derated to 125% of the continuous load. This means that the conductor must be sized to carry at least 125% of the load current. For example, if a continuous load is expected to draw 80 amps, the conductor must be sized to carry at least 100 amps. This derating ensures that the conductor will not overheat and that the insulation will not break down, which could lead to a short circuit or fire. Secondly, high ambient temperatures can also affect the current carrying capacity of conductors. The ambient temperature is the temperature of the air surrounding the conductor. When conductors are installed in areas with high ambient temperatures, they are less able to dissipate heat, which reduces their current carrying capacity. The National Electrical Code provides tables that list the ampacity of conductors at different ambient temperatures. These tables must be used to derate conductors when they are installed in areas with high ambient temperatures. For example, if a conductor is rated to carry 100 amps at an ambient temperature of 30 degrees Celsius, it may only be rated to carry 80 amps at an ambient temperature of 50 degrees Celsius. Thirdly, the number of conductors in a raceway can also affect the current carrying capacity of conductors. When multiple conductors are installed in a raceway, they generate heat, which reduces their ability to dissipate heat. The National Electrical Code provides tables that list the derating factors that must be applied when multiple conductors are installed in a raceway. These derating factors depend on the number of conductors in the raceway and the type of raceway. For example, if 3 current carrying conductors are installed in a conduit, the ampacity of each conductor must be reduced to 80% of its rated ampacity. Fourthly, the type of overcurrent protection device used to protect a circuit can also affect the size of the conductors required. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The National Electrical Code requires that conductors be protected by overcurrent protection devices that are sized to protect the conductors from overloads and short circuits, meaning it must be able to handle the let-through energy. The size of the overcurrent protection device must be based on the ampacity of the conductor. For example, if a conductor is rated to carry 20 amps, it must be protected by an overcurrent protection device that is rated no higher than 20 amps. Fifthly, different conductor materials have different temperature ratings and may require different levels of derating. For example, copper conductors have a higher temperature rating than aluminum conductors. This means that copper conductors can carry more current than aluminum conductors of the same size. The National Electrical Code provides tables that list the ampacity of conductors made of different materials. These tables must be used to select the correct conductor material for the application. Now let's go over calculating conductor ampacity. Calculating conductor ampacity involves several steps to ensure the selected conductor can safely handle the intended electrical load under specific conditions. Here is a breakdown of the process. Firstly, determine the load current. Calculate the total current the conductor will need to carry. This involves summing up the currents of all devices and equipment connected to the circuit. For motors, use the full load current of law found in the motor nameplate or in National Electrical Code tables such as Table 430.250 for single-phase motors and Table 430.251 for three-phase motors. Secondly, apply the continuous load derating. If the load is considered continuous, which means it operates for 3 hours or more, multiply the load current by 1.25, which is 125%, as required by the National Electrical Code Section 210.19. This derating accounts for the additional heat generated by the continuous operation. Thirdly, determine the base ampacity. Refer to the National Electrical Code tables such as 310.16 to find the ampacity of the conductor based on its size and insulation type. This table provides ampacities for conductors at a standard temperature, typically 30 degrees Celsius, which is 86 degrees Fahrenheit. Choose the conductor insulation type based on the application and environmental conditions. Common insulation types include THHN, THHW, and XHHW. Fourthly, apply ambient temperature correction. If the ambient temperature exceeds the base temperature of the ampacity table, you must apply a correction factor. These correction factors are listed in tables associated with the ampacity tables, such as those found in the National Electrical Code 310.16. Multiply the base ampacity by the correction factor to obtain the temperature-corrected ampacity. Fifthly, apply adjustment factors for the number of conductors. When multiple current-carrying conductors are installed in a raceway, cable, or conduit, they generate heat that can reduce the ampacity of each conductor. Apply adjustment factors based on the number of current-carrying conductors, as specified in the National Electrical Code Table 310.15. Multiply the temperature-corrected ampacity by the adjustment factor to obtain the final derated ampacity. Sixthly, select the conductor size. Choose a conductor size that has an ampacity equal to or greater than the calculated derated ampacity. Ensure that the selected conductor meets all other requirements of the National Electrical Code, such as those related to voltage drop and termination temperature. Seventhly, verify overcurrent protection. Select an overcurrent protection device, such as a circuit breaker or fuse, that is sized to protect the conductor. The overcurrent protection device should have a trip rating that does not exceed the conductor's ampacity. For motor circuits, the overcurrent protection device must comply with the National Electrical Code 430, which allows for higher ratings to accommodate the motor's starting current. Eighthly, document calculations. Keep a record of all calculations and derating factors used to determine the conductor size. This documentation is essential for inspections and future reference. Example: let's calculate the conductor size for a 100 horsepower, 3-phase motor with a full load current of 124 amps, operating continuously in an ambient temperature of 40 degrees Celsius, with 3 current-carrying conductors in a conduit. Firstly, calculate the continuous load current. Multiply the motor's full load current by 1.25. 124 amps times 1.25 equals 155 amps. Secondly, determine the base ampacity. From the National Electrical Code Table 310.16, A number 1 THHN conductor has an ampacity of 170 amps at 30 degrees Celsius. Thirdly, apply the ambient temperature correction. The correction factor for THHN insulation at 40 degrees Celsius is 0.88. Multiply the base ampacity by the correction factor. 170 amps times 0.88 equals 149.6 amps. Fourthly, apply adjustment factors for the number of conductors. With 3 current carrying conductors in a conduit, the adjustment factor is 0.80. Multiply the temperature corrected ampacity by the adjustment factor. 149.6 amps times 0.80 equals 119.68 amps. Fifthly, select the conductor size. Since the calculated ampacity of 119.68 amps is less than the required 155 amps, we need to choose a larger conductor. A number 3 THHN conductor has a base ampacity of 225 amps. Recalculate with the number 3 conductor. Apply the ambient temperature correction. 225 amps times 0.88 equals 198 amps. Apply adjustment factors for the number of conductors. 198 amps times 0.80 equals 158.4 amps. The final derated ampacity for the number 3 THHN conductor is 158.4 amps, which is greater than the required 155 amps. Sixthly, verify overcurrent protection. Refer to the National Electrical Code 430 for motor overcurrent protection requirements. Select an appropriate circuit breaker or fuse size based on the motor's full load current and the National Electrical Code guidelines. Remember to consult the latest edition of the National Electrical Code and follow all applicable regulations and guidelines for conductor sizing and derating. When in doubt, consult with a qualified electrical engineer or electrician.